Hi everyone, I'm Marc. Thanks very much for checking out this video. This is joint work with Jacob Focke from the CISPA Helmholtz Center for Information Security at Saarland Informatics Campus. As you see in the title, in this work we are interested in the complexity of counting small induced subgraphs in very large host graphs. Let me start by setting up the notation and defining the family of problems we are interested in. So first of all, given a computable graph property phi, a positive integer k, and a graph g, then this set in sub phi k to g just contains all k vertex induced subgraphs of g that satisfy phi. And formally, this contains all subsets of the vertices of g of size k that induce a graph that satisfies the graph property phi. Since we will be interested in counting those, let me introduce this notation for functions. So I will write sharp in sub phi k to the star for the function that expects as input a graph g and then outputs the cardinality of this set. That is the number of k vertex induced subgraphs of g that satisfy the property. And note, due to the generality of this definition, this encodes or models a variety of counting problems that have been studied before. For example, if phi is the property of being a complete graph, then this function counts k-cliques. Or if phi is the property of being a cycle, then this function counts k-vertex induced cycles. And due to this generality, it's not surprising that we are not the first ones to study this problem. In this generality, it was introduced by Jeremy Meeks a couple of years ago. So let me give you one more concrete example. If G is this graph here, if phi is the property of being bipartite, and if k is equal to 4, then we would count induced subgraphs like those two, both are bipartite and of size 4, but we would not count this one or this one. So both contain a triangle and are hence not bipartite. And note that this also illustrates that we really need to include all edges. So after we selected 4 vertices, we need to take all edges between them. So we are not counting subgraphs that satisfy the property, but we really count induced subgraphs that satisfy the property. Now, if you fix a graph property phi, this defines a computational problem, which we call sharp in sub phi. And the input of this problem is a pair of a positive integer k and a graph g. And the output is the cardinality of the set. That is, again, just the number of k-vertex induced subgraphs of G that satisfy phi. And the goal of this line of research is to find out for which properties phi this problem is easy and for which it is hard. And if I say easy or hard, you might think of polynomial time tractability versus sharp p hardness, where sharp p is a counting equivalent of NP. If you don't like sharp p hardness, you could think of lower bounds under the exponential time hypothesis that rule out polynomial time algorithms. But you might recall from the title of this talk that we are actually interested in the cases where the induced subgraphs are significantly smaller than the graph. And this means we actually expect or want to consider inputs in which k is much smaller than g. And therefore, we lack the requirement of searching for a polynomial time algorithm. And instead, we only search for an algorithm that runs in time f of k times a polynomial in the size of g. And f may be any computable function. It might be super polynomial, even exponential. And again, the idea is that for k that are significantly smaller than g, even an algorithm that runs in, say, time 2 to the k times polynomial in g might still be an efficient algorithm. And if you're familiar with parameterized complexity, then you will remember this as fixed parameter tractability. That is, let me equip this problem here with a parameterization. I will just choose k as the parameter. And then the question whether an algorithm with this running time exists is equivalent by definition of asking whether the problem is fixed parameter tractable. And so now more precisely, when I say we want to find out for which properties the problem is easy and for which it is hard, we actually ask for which properties the problem is fixed parameter tractable and for which it is not. And then ruling out fixed parameter tractability, you can again try to prove lower bounds under ETH, but you could also try to prove sharp W1 hardness, where sharp W1 is kind of a parameterized counting equivalent of NP. So in particular, if you show a problem sharp W1 hard, then the problem is not fixed parameter tractable unless ETH fails. Now let me give you some examples of graph properties that make the problem easy or even very easy. First, this is very boring, so if phi is the property of being either constant true or constant false, then this problem is trivial, because we either output number of vertices, choose k, or just 0. But also if we consider properties like having an even number of vertices, while this is not a trivial graph property, it still makes this problem trivial. Because on input g and k, we just have to check whether k is even. If that's the case, we output number of vertices choose k. And if it's not even, then we just output 0. And with this, for the same reason, the property of having at most 42 vertices also yields a very easy or even trivial problem. And what those examples have in common is that in each case, the property, if you fix k, the property is then either true or false on all graphs with k vertices. And if we generalize this idea a bit, we get the notion of meager graph properties. And I will call phi meager if there is a constant b, such that for every k larger than b, phi is either constant true or constant false on all k vertex graphs. And this means the property becomes eventually trivial in the sense that from some particular point on, the property is always constant true or constant false on all k vertex graphs. And generalizing the examples we have seen before, it is very easy to show that sharp in sub phi is fixed parameter tractable if phi is meager. And from now on, I will always assume that phi is also a computable graph property to avoid talking about non-uniform fixed parameter tractability. So we want to exclude properties like the property is true if the number of vertices in binary encodes a halting Turing machine. So we don't want to talk about this. So just computable properties. And now meager properties are very boring, but we actually, let me recall that fixed parameter tractability means f of k times the polynomial in G. And in some cases, we really only get FPT-ness, but we get polynomial time algorithms for most natural properties. Now, we actually assume that in all other cases, the property is hard for sharp W1. And recall that sharp W1 is a parameterized counting equivalent of NP. So under ETH, this rules out FPT algorithms. So in other words, we really think, and we have evidence for that by now, that whenever phi is not meager, you cannot hope for an efficient algorithm. And this is very bad news, because it means you need to do something like approximate counting or restricting the graph G if you want non-trivial efficient algorithms for those kinds of problems. Now let me talk a bit about previous work on this problem. And one of the most important results, quite recent, 5 years ago, Focke, Dell, and Marc proved an implicit classification or an implicit structural complexity dichotomy. And what they did is they proved that for every property phi, this problem is either fixed parameter tractable or sharp W1 hard. So there are no Lardner-like intermediate cases. So you won't find a property phi for which the problem is neither FPT nor sharp W1 hard. And what we would like to do is to use this implicit dichotomy to prove that whenever we have a non-meager property, that we are actually in this sharp W1 hard cases. And then again, under ETH, this would prove the conjecture. Perhaps let me emphasize this once more when I say an implicit dichotomy here. This means that even though we know in this theorem that we are always either FPT or sharp W1 hard, it's not clear at all to pinpoint the complexity if you give me a concrete property. So if you give me a concrete property, I know the problem is FPT or sharp W1 hard, but it can be really hard to find out for a particular property whether it is actually FPT or hard. Then again, as I said before, we would like to show that the non-meager properties are actually the hard ones. And for some classes of properties, this was achieved in the past. So the first more general class of properties that was investigated for this problem is the class of all minor closed properties. And a property is minor closed if it's closed under vertex removal, edge removal, and edge contraction. For example, the properties of being planar or acyclic are minor closed. And Jeremy and Meeks, a couple of years ago, and among others, they proved that this conjecture is true. Again, we always assume ETH if phi is a minor closed graph property. And then the next step is to consider like a bit more general class of properties. And what was done in the past is that, we looked at monotone properties. And those properties are closed under vertex and edge removal, but not necessarily under edge contraction. So examples for monotone properties that are not minor closed are the properties of being bipartite or triangle free. And 2 years ago, we showed that the conjecture is true if phi is a monotone property. Now, continuing like that, you can start investigating edge monotone properties or hereditary properties. Edge monotone properties are the ones that are closed under the removal of edges, but not necessarily under the removal of vertices. For example, the property of being disconnected or the property of having fewer edges than vertices. Both of those are closed under edge removal, but both are not closed under vertex removal. So they are edge monotone, but not monotone. And for edge monotone properties, there is a bunch of results by now, and I claim that all natural properties are actually covered. So if you give me any natural edge monotone property, I'm quite confident that I can find hardness in one of those works. But we still did not manage to prove hardness for all non-meager edge monotone properties. And the reason for this is that for edge monotone properties, you actually have to solve some conjectures and open problems about topological properties of edge monotone graph properties. So I think we are quite far away for classifying or for proving the conjecture for edge monotone properties. If you're interested, you can check out this work in the poster session. So we have examples of edge monotone properties where we don't know the complexity. So we don't know whether we have non-meager edge monotone graph properties where we were not able to prove hardness yet. But they are very artificial. In this work, we actually focused on hereditary properties, and those properties are closed under vertex removal, but not necessarily under edge removal. So, for example, being chordal or hole free are properties that are closed under the removal of edges, but not under, they are closed under the removal of vertices, but not under the removal of edges. So they are hereditary, but not monotone. And 2 years ago, we were able to partially resolve the conjecture for hereditary properties, but only for those that had a single forbidden induced subgraph. And in this work, we finally solved the case for all hereditary properties. So let me state our main theorem explicitly. We prove that given a hereditary graph property phi, if phi is meager, then sharp in sub phi is not only solvable in FPT time, but it's actually polynomial time solvable. And in all other cases, we prove sharp W1 hardness, but also a tight lower bound under ETH. So we prove that if ETH is true, there is no function f such that you can solve the problem in time f of k times the size of g to the smaller of k. And this means that the exponent must be linear in k. So the brute force algorithm runs roughly in time f of k times the size of g to the k. And this lower bound means you cannot decrease the exponent to a sublinear function. Note that you can be a bit better than the size of g to the k by fast matrix multiplication, but this result tells you that if you believe the ETH, you cannot get a sublinear exponent. So let me spend the last part on this talk by giving a rough overview of the techniques. I will keep this quite general, and for more details, again, I hope to see you at the poster session if you have questions or want to see more about this. But yeah, so let me very roughly start by giving you the two main ideas we needed to prove this. And the first one is an approach that was that we used in almost all of the previous papers. What we did is we translated the problem into the so-called homomorphism basis. And by this I mean that whenever we fix phi and k, then we can express this function, which counts k vertex-induced subgraphs that satisfy phi, as a finite linear combination of graph homomorphism counts. And yeah, this means that if you evaluate this function on a graph G, this is equivalent to, on input G, computing this linear combination, so taking the sum from I equals 1 to L, this coefficient AI, times the number of graph homomorphisms from HI to the input. I won't define what a graph homomorphism is, since we only use them in a black box manner here. But let me emphasize those coefficients AI and the graphs HI, they only depend on phi and k, but not on the input. And the reason why this homomorphism basis is useful is a result due to Kutekapian and Marc, which they used towards their implicit dichotomy. They proved that whenever in a finite linear combination of homomorphism counts, we find a graph HI with large tree width and with a non-zero coefficient, then computing the entire linear combination is computationally hard. And again, I won't define a tree width formally, just think of it as being a notion on how tree-like a graph is. So trees have tree width 1, cycles have tree width 2, and cliques have maximum tree width. So with this result at hand, the general attempt we used in the last works was the following. So we fixed a property that was non-meager, or we showed that for any property which was non-meager. We wanted to prove that for infinitely many k, a high tree width graph survives in this linear combination, which is, by the way, unique, and which also has a non-zero coefficient. However, the problem is, and this was also apparent in the latest works, is that those coefficients are very hard to control. So they are very often alternating sums, so sum over an index I minus 1 to the I times something, and proving that those are non-zero can be very hard and challenging. And for hereditary properties, we were not able to resolve the complexity using this attempt. And we instead took a sidestep, and this is our second main ingredient, which is the bipartization of the problem. So let me assume that bipartite graphs have a fixed left-hand side and a fixed right-hand side. And then a bipartite graph property is a function from bipartite graphs to 0 or 1, which is invariant under isomorphisms that map left to left and right to right. For example, if consider the property of having left degree smaller than 3, this is not a graph property because it might be not well defined. So we might have no bipartization, no left and right bipartition at all, or we might have multiple. So this really requires that we fix left and right hand side. And then the green graph here would satisfy this property, and the red graph wouldn't satisfy this property. And what we did is we proved that for every hereditary graph property, there is an equivalent bipartite graph property. And by equivalent, I mean it has the same complexity than our initial property. That is, counting induced subgraphs of size k that satisfy the hereditary property has roughly the same complexity than counting in bipartite graphs, bipartite induced subgraphs that satisfy this bipartite graph property. And now if you know the bipartite double cover, you might think we did just that, but it was actually much more involved than just taking the bipartite double cover. We had to heavily rely on the structure of the forbidden induced subgraphs of the hereditary property. So this does not generalize at all to arbitrary graph properties. And unsurprisingly, we also used Ramsey's theory. Again, if you want to see more details about this, feel free to drop by the poster session. But with that done, we then, having this equivalent bipartite graph property, we translated the bipartized problem into the homomorphism basis. And then we were able to prove that the bicliques, so complete bipartite graphs, survive with a non-zero coefficient. And we were able to do that by generalizing earlier work on this problem. And since bike leaks have unbounded tree width, we were able to prove hardness and even our ETH lower bound using this approach. So that was only one slide on the techniques, but in general, those two ingredients, so the homomorphism basis and the bipartization, those were the main two steps in proving this result. So let me conclude with like some obvious open questions. So with hereditary properties we solved, the first next step I suggest is to tackle edge monotone properties. But as I said before, for edge monotone properties, you have to answer some hard questions about topological properties of edge monotone graph properties. So that might be, actually, I think that might be very challenging to resolve all edge monotone properties. But if we succeed in that at some point, then the goal is, of course, to prove the conjecture in full generality. And after this is done, we really know for sure that if you want to count small induced subgraphs in a large graph with any interesting properties, you always have to either relax to approximate counting or to restrict your host graph, because in the unrestricted case, you will never be able to significantly beat the brute force algorithm, at least if you believe in ETH. But yes, that is everything I wanted to show you in this video, and I hope I see you at the conference. Thank you very much.